Hello, my name is Frederik Baucks, and in our work we study the question of how can we detect and quantify difficulty variations in an education curriculum over time, which is an open problem in the curriculum analytics domain. In particular, we address this question by adapting item response theory and show it can yield valuable insights for curriculum analytics. Our goal is to measure whether and how course changes over time in terms of difficulty. The motivation for this is the equality and thus comparability of student cohorts to consistent teaching. If this is not the case, the same student might perform differently in different cohorts. And we have found that previous work assumes that courses are time invariant. Therefore, this presentation addresses the tracing of course difficulty over multiple years, and to do this, we use item response theory, IRT. Curriculum analytics studies curriculum-related data, intending to understand, modify, and improve educational programs, such as our college degree. The role that IRT can play in this process is motivated in the following. We assume a curriculum consisting of a number of courses offered rapidly in different semesters. We use the term course offering to refer to one course in one semester. The idea underlying IRT in our context here is to assign each student a latent trait value, student ability theta I here, that explains the probabilities with which the student passes individual course offerings. The relationship between student trait values and course offering pass rates can be modeled by fitting a sigmoid function for each course offering. And this is known as the item response function, or IRF, as you can see on the right-hand side. The position of the IRF on the x-axis is the value where it has its largest slope, and it indicates the course offering's difficulty, and we denote it with delta J. The slope of the IRF describes the course offering's discrimination property, and we denote it by alpha J. So given a student trait theta I, course difficulty delta J, and discrimination alpha J, we define the probability of passing a course offering J by the known sigmoid function on the right-hand side. So note that we here estimate one difficulty parameter for each course offering because we want to trace the changes of them. The resulting model is called a Birnbaum model or two-parameter logistic model. And if we fix here all alpha j's to 1, it is called a rush model. To evaluate the suitability of IRT for curriculum analytics, we need to assess whether students' multi-year course response data meets IRT's theoretical assumptions. First key assumption is unidimensional student trait. That means a student's probability of passing different courses can be explained by a single latent trait that stays constant over time. The second key assumption is local independence. This means that the performances of a single student in different courses are independent of each other, given his or her latent trait value. So to check these two assumptions, it is important that we take a closer look at our performance data. Our used CS dataset, computer science dataset, consists of 664 students attending 19 courses, resulting in 127 unique course offerings over 9 years. So let's look at our data in the following. One key assumption is tackled in the model selection. In the model selection process, we examine the data and model fit of different models to decide on the dimensionality, which was the first key assumption, and select a model. One method to investigate the underlying dimensionality of our data is the scree plot and principal component analysis, or PCA, applied to the student's performance data. We see the former scree plot on the right-hand side, and the scree plot suggests here that one dimension may be sufficient to explain the data. In addition, PCA has shown that the first principal component can already account for 60% of the variance in the data. We therefore investigate 1- and 2-dimensional models in the second step. For this, we use the information criteria, Archaike information criterion, AIC, Bayesian information criterion, BIC, and sample size adjusted Bayesian information criterion, SABIC. These compare the number of model parameters with the model fit so that we can decide for a model in the following. While the lower AIC score here indicates that the 2-dimensional Birnbaum or two-parameter logistic model is preferred, the lower BIC and SABIC scores, which are more conservative regarding the number of model parameters, indicate that the rush model is more suitable. In addition, the Rush model performs better than the Birnbaum model in all three criteria. Thus, we focus on the Rush model in the following experiments. Now that we have decided on the model, let's look at the validity of the model parameters. We compare the student trait with the grade point average and the course offering difficulty with the pass rate of the respective course offering. So do the parameters capture the information that we are interested in? Both correlations here show strong statistically significant correlation, and that is the parameters seem to measure what we expect them to measure. In addition, the figure with the course offering difficulties, here we have colored in red exactly those offerings that lie in the pandemic period between 2020 and 2022, and these accumulate at the very low course offering difficulty. In addition to validity, we consider the reliability of our model to assess whether the results are robust. In the simulation study, we test how much data is required to ensure a reliable Rush model parameter fit. We observe small root mean square error values and high correlation values even for a small number of students, indicating that we can achieve a satisfactory model fit using small scale data, as you can see in the figure on the right-hand side. Finally, let's look at the model parameters. Here we have mapped the course offering difficulties for 3 representative courses. The sorting of the offerings within a course is from the top in the earliest semester to the bottom in the latest semester. We see courses can have stable difficulties, but also changing ones. Especially we see difficulties fluctuate in the programming course here, as well as difficulties becoming smaller or more negative in computer science too over the time here. The course offerings marked here in red are pandemic offerings, as before. And overall, we observed a systematic lowering of difficulty of the courses during the pandemic period. But not only courses can change their difficulty, also the students in the course offering can differ. We calculated here an adjusted pass rate for the 19 courses based on the average latent trait of the students. Interestingly, this shows that the pass rate is corrected upwards in courses of the first semester and corrected downwards in courses of the following semesters. This is probably due to the dropouts between the first and the last semester. Here in the first semester, and here in the last semester, for example. In summary, we have seen that IRT can be a reliable method to provide valid results. The parameters have shown us that course offering difficulties do not have to be stable over time. We even found that course offerings can be strongly influenced by external factors, such as the pandemic. In future work, we would like to investigate our methodology in other settings and expand the range of IRT models used here. Thanks for listening.